Hi students, hope you guys are doing well today. I am really curious to know how your concept models are going. I'm also really hoping that some of you choose one and some of you choose the other. I think we'll see where it settles out. I think my chances are pretty good that if you did a coin flip 16 times, you wouldn't get all heads. We'll see. Don't forget you have 2 weeks to do your concept model. I mean, half of that first week is already gone, but that's not a 1 week assignment, that's a 2 week one. So you can still do these videos, watch the discussion boards, do the regular assignment. And I really do think the regular assignment this week is actually probably a little more brief than usual. And I don't know about you, but I just like spreadsheets. So when I'm doing spreadsheet assignments, I just feel like the world is my oyster, kind of in my happy place. Some of my most exciting evenings are when my wife says to me, I want you to teach me this thing on the old spreadsheets, and that's more information than you wanted, but it's true. It's true. Spreadsheets are cool. We will keep working. I'm actually using the same spreadsheet that I had last video, the one titled here, Composite Area Calculations. And what I'm really just going to do today is work through the problem on page 139 of the textbook. Okay, the one that has the like triangle shape. In fact, here let's put it in. Let's grab that image. We are going to pop this in. Sorry that you had to see all that. Oh wow. Okay. Hold on. That was the exact opposite of what I meant to do. Not in the cell, but on top of the cell. Okay, there we go. So you have this in your textbook, of course, but this is the one I'm talking about. We're going to pick this apart bit by bit. There is so much going on here, but I'm confident that if we just tackle this one, and I show you, that'll be even more than you need to be able to do the assignment that you have for this week. All right. Before I go into this more complex one, let me just give you one that might be a little simpler. What am I doing? Insert image over cells, and we're going to do this one right here. This actually looks like the logo of a contractor here in Santa Barbara, by the way. I think it's called Whole House Construction. So, this is a little bit of a refresher from last week. Can we work out the composite area of this shape using spreadsheets? I'm going to build it all 100% from the start. So apologies if this goes too slow for you, but I want you to see, like, look over my shoulder as to how I do this. So, and you know, I'm not even looking at what I did last week. So if I choose like some slightly different names and you know, table designations and things, that's not intentional. It just shows that, you know, every time you sit down and do this, you might do it slightly differently because you think of different things and you get better in your ability. So I'm going to label the different shapes. I'm going to identify three shapes in this one, or 3 regions. I'm going to say we have our triangle on top, we have a square, and then we have a hole in the middle. And the big thing that's going to be important here is that the area of the hole is going to be negative. And just because I'm getting fancy, I'm going to turn off grid lines. I just think it's a nice clean look. I'm going to embolden my thing. I like to put a little bit of color. I really do think that it helps. That's a horrible, that color is just too much of nothing. That's too dark. Light blue. There we go. All right, shape. And then, okay, I think I'll still call it dimension 1 and dimension 2 because I know I'm going to be dealing with different types of things. So, and these will be measured in meters, because that is what is in the diagram. Okay, so my triangle on top has a base of 40 meters and a height of 20 meters. And before I go any further, I'm going to select those, do paint format, and drag over there. And I actually want centered. Okay, and I can't see everything here, so I'm actually going to grab those, and then, oh, let's do a few more. I'm going to make it a little wider, just a little wider until I can see everything nice and neatly. Okay, very good. Okay, the square's dimensions are also 40 and 40, as it happens. And now the hole in the middle. Now this is where arguably, you know what, okay, I have another idea. Let's do it this way. Let's say base, let's say height, and let's make another one. Let's say radius, also in meters. I guess I could predict that there's more coming up. Let's just do them. So what is the radius of this circle? Notice that I'm not going to use all the cells in this table because they don't all apply. If you look at this diagram, you see a little symbol. It's a circle with a diagonal line struck through it that like extends out to both sides of that circle. That symbol means diameter. Okay, it's like a rough, simple picture, I guess, of a circle with a dimension line through it. And because it's like all the way through from edge to edge, it's the diameter, not the radius. However, as I said in the last video, circles are really defined by their radii, not by their diameters. So I'm just going to like interpret. I'm just going to put the 10 right there. I did that mentally, and that is perfectly fine. It's half of that 20. You could also do it in diameter, but radius is the way to go. And now we put in our formulas for, let's work out the areas measured in meters squared. This is going to be the base times the height. Remember, you use asterisks for multiplication, not x's. And I typed in, sorry, I didn't even type, I clicked on the cell references. I didn't type in 40 times 20. I clicked on the cell references, and the reason is that if that changes, that value will change. This one here is going, oh, I messed it up, didn't I? Formula for a triangle is half base times height. Okay, 0.5 times those two. I was getting muddled there. The rectangle, all rectangles, including squares, a square is a type of rectangle, are base times height. And circles are pi, and then you do open, close. That's it. Pi, open, close, parentheses. Pi times radius squared. See that? Pi times radius squared. Pause the video if you need to focus on any of this. And we get that, and I think that's way too much precision, so I'm going to turn it down up here. I'm just going to go to the, let's do the nearest whole number. Even that is more than we can really justify because everything else here was given in 1 or maybe 2 significant figures. All right. Now, I suppose for what we did up to yesterday, that is actually all you need, isn't it? Okay, so we actually don't need this column. You can do reset, you can do clear, and then the left one, there we go. And now I did total area. And remember, I used the sum. It actually suggested it to me. Did you see that? Even as I was typing, it suggested, hey, do you think you want to sum these? Yes, I do. I can take the suggestion. It's good. Make sure it tells you what you actually want. Some of those other suggestions did not. And then I'm going to turn the precision down again and clean up some formatting. Excellent. And I should always do units. You have to become a unit aficionado. You got to become a stickler for units. Please do that if you're not already, as soon as you can. Always want units for physical problems. All right, so this is our thing. Now, what I would like to do as well, I'd kind of like to get a common sense validation. What I mean by that is, I know I have an answer, but what if I typed a formula wrong? What if there was a typo, or I don't know, maybe I clicked on a suggestion for a formula, but I shouldn't have? How can I know if 2,316 is a reasonable answer? So here's what I'd say. I like this approach. The maximum possible area that this could be would be, like, imagine that the whole thing was just one great big solid rectangle with a base of 40 meters and a height of 60, like the whole height, the 40 plus the 20. Imagine all that fancy whole house being just replaced with a rectangle. The area of that would be 40 times 60, like I said, 2,400. Okay, so because I have like cutouts, it's a triangle on top, not solid, it's a circle in the middle, not filled in, I know that my area can't possibly exceed 2,400. Now, what is my minimum possible area? Well, that's an interesting question. It's hard to kind of say a minimum, because I guess your minimum would be 0. We know it's not 0. Man, I could even like count squares. Each square I know is 10 times 10, 100 meters. So I could kind of count rough filled in squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've got definitely have 16 filled in squares. Each square stands for 100 because it's 10 meters by 10 meters. So I know that my shape must be more than 1,600. Okay, I did that by counting squares. I did this one by saying giant solid rectangle. So what do we think? It's got to be less than 2,400, more than 1,600. Do we like our answer of 2,314? Well, yeah, like it's in between those two, but it seems a little close to 2,400. It's almost 2,400. It's just, in fact, what is it? I love spreadsheets. Look at this. It is that number divided by that number. It's 96% of my absolute max. I don't think that's right, because I've got triangular cutouts on top. I've got a circular cutout in the middle. Something feels wrong. Did anyone spot it? And I'll be honest, I actually made a mistake here as I was going. I see it now, but I didn't see it when I was working. Good thing I did this common sense validation. My mistake was that the hole in the middle was supposed to be negative area. That was it. It's a blank space, so I need to put a negative in front of that equation. Negative pi radius squared. Ah, that's better. Look at that. Now it's subtracted, and when you do the sum will count negatively, any negatives. It can add negative numbers. It doesn't just blindly add everything as positives. That's better. I knew it was a little more than the 1,600, and I was pretty sure it had to be a lot less than the 2,400, although that was an absolute upper bound. That's great. Happy with that. I'm even going to mark that in green because I'm feeling confident. Okay. There we go. All good. All right. That was a little 15-minute warm-up for the day. Let's now focus in on the actual problem that we want to tackle. Oh dear. Hold on. Sorry, I was trying to get rid of some stuff. There we go. Just clearing the area. Okay. All I will do is work through what the book says, And actually, I need to say now that there's a really important formula that we're about to use. It was listed, it was given on page 137. I didn't really mention it yet, but it's really important. I'm going to insert a picture of this right now. And make that a lot smaller. Come on. There we go. Okay. Wow. Could you be looking at anything more complex, right? Between the diagram and those two formulas there, bear with us. We'll sort this out. This is simply more of the old sigma notation. But I know there's a lot of symbols and things floating around. So first of all, let's pick this apart. So first of all, you have what we call x bar, and we have y bar. That is how you say that. Okay, B-A-R. That's the x with the line across the top and the y with the line across the top. That refers to the overall centroid coordinates. Okay, like the x and y coordinates of the whole thing, the centroid of the whole shape. Which, you know, you've already got the answer if you want it in the book. They actually give you x bar over on the next page as being 5.57 inches. We're going to confirm that soon. But that is what that refers to. If you want to find the x and y coordinates, that's what you're looking for, x bar and y bar. What else do we have in there? We've got a lot of sigma notation. Sigma, remember, just means to sum a list of numbers, okay, adding things up. And they really go for it here. This is the precise sigma notation, not the general idea like sigma f equals 0, but the precise one. So they used the little letter I, and letter I did say this before in other videos, but it's a counting variable. It's a placeholder. Okay, it is not a fixed constant. It's a little placeholder that counts off from I equals 1 all the way up to I equals n. N is simply the number of objects that you are summing. In this case, we are going to have three areas, 3 shapes, or let's say three subshapes in our example. So for us, n is going to be 3. And then the letter I is going to count off from 1, 2, 3. And this seems like a lot of notation just to express those simple facts, but you know, that's we try to have robust formulas that could get more complex if they need to. X with the little I down the bottom. Actually, sometimes that's written like that. X with a subscript I, that is the individual, I should say X centroid of the subshape. Yeah. And then A subscript I is the individual area of the subshape. Okay. So that defines everything we're about to use here. I'll leave that there on the screen. You can keep referring to that. I kind of like working out of a spreadsheet. Have I mentioned that I like spreadsheets? Okay. Let's get into this. So I am going to build the exact same table. I will do it all over again just to show you how we do this and how quick and easy it really is. I'm going to call it subregion this time, or subshape. Subshape, that's the term I was just using. So we have, for this more complex, you know, arrow thing with a hole in it, we have 3 things. We have the triangle on top. We have what looks to be, yeah, it's a little square underneath. And then we have a circle. I'm just going to write cutout so I don't forget this time. It's a cutout circle. Actually, as it happens, that is exactly the same as what we just had. Triangle, square, hole. Coincidence? Yes. Yes, it is. Sorry, there's been a little too much Phineas and Ferb in our household this summer. Alright, I like bright colors, that's good. I like bold. Alrighty, what's next? Let's paint some areas. Subshape. Okay, so the next one was, let's do base. And we are measuring in inches. And then we got the height of our different shapes. And I kind of like this way, actually. I'm going to settle on this. I'm going to define bases, heights, and radiuses, just radii, just knowing that I won't use all of them for every shape, because it won't apply. Okay, the base of the triangle, that's where we're looking, where it says region 1. This is the author, what's his name? James H. Allen III. He is showing those 3 subshapes one by one. That's what it means when it says region 1, region number 2, region number 3. I don't know if it's necessary to do all that. It might just be more information than you need, but that's what he's trying to show. So, I guess it would be a very complex diagram otherwise. The base of the triangle is 8 inches. The height of the triangle is also 8 inches. Oops. The area of the triangle is, I won't forget it this time, half times base times height. By the way, when taking notes this week, I don't know if you've already realized this, maybe you did, but it probably makes sense to take notes in a spreadsheet. Just copy what I'm doing, unless this is incredibly familiar to you. Base, height, both 4, no radius. That one times that one. Could do that. Okay. The circle, the radius of the circle. Now we've got to read really carefully. In this case, they actually said the words 1 inch diameter hole. That's what that means. Okay. 1 in dia hole. I think you would have gotten what that meant even if I hadn't said it. That is a 1 inch diameter hole. So they didn't use any symbols, they just put the words there. Okay, so I want the radius though. There you go, which is half of that. I want pi times the radius squared, and oh look, I just remembered it's a cutout, so I'm making it negative. Negative pi times the radius squared. Way too much precision. Okay. Now, this little set of data here, this is exactly what is in table 11.1 at the bottom of page 139. That's the 3 numbers they have there, where it says 0.5, parentheses 8, parentheses 8, equals 32.00. That's my number right there. Parentheses 4 equals 16, and then negative pi, parentheses 0.5 squared, and there it is, okay? So I know I'm laying out my table differently, but he's kind of showing a bit of a summary of things. So all that I have is in that one column. And then he also has, underneath it, he has total. And this time I'm actually I'm gonna make like a whole row of totaled things, and then I will I'll have some different totals, I think. What do we want? We want the sum of those things. All right, again, that accords perfectly. I feel bad doing any more than 3 significant figures because the whole problem was given in 1, wasn't it? But it's okay. All right, 47.2. Up to that point, that is what we did last video and this video. Now we're going to go the extra step. This is where you buckle in for the ride. This is where we're going to use those X bar and Y bar formulas in the green down there. So I hope you are ready. It's going to be fun. I'm looking forward to it. We got to list off some things. So the first thing to list, and you know what, I'm actually going to, once I change from dimension 1, those words got a little shorter. So I'm just going to sneak things in there. Make my columns actually work for me, because I think I might need some more. Okay. I am going to list off now the X centroids, and using the author's terminology. So this is X subscript I. This is the centroid location, the X centroid. Remember, there are always 2 coordinates. The X centroid of these individual shapes. And these are measured, they are lengths. They are measured in inches. Okay, X subscript I. This is the X subscript I down there in the green. The individual X centroid of the subshape. And this is not too hard, but you just got to read off. Remember, we're doing everything relative to the one consistent origin which has been set. I'm going to write that in there. One consistent origin for the entire problem. That is critical. I cannot highlight that enough. If I could make that flash, I would, but I don't know how. So please stick with that one consistent origin for the entire problem. So the X centroid for the triangle, because that's what we're dealing with first, is going to be, how good is your memory? It's 2/3 of the base. Look at that little preview, 5.3 repeated. It's trying to help me out. 2/3. Remember I said with right angled triangles, you have this on page 138 or in your notes. For right angled triangles, your centroid is located either 2/3 of the way along from the sharp end or 1/3 of the way back from the thick end. And because we are measuring from the origin, we have to say it's the 2/3. Okay, that's that X1. It's a little fuzzy on the screenshot, but it says X1 on that region number 1 diagram. So that is 5/3. I'm just going to, well, we'll adjust at the end. 5/3, sorry, 5 1/3 out of the total 8 inches of the base. For the square, the X centroid of the subshape, the square, is going to be, now I can decide what to do here. I'm going to say, I can do it like this. I'm going to say 4 inches plus half of the base. Now look at what I'm doing there. I'm saying the first 4 inches, the 4, it's that white gap from the origin to where the square actually begins. And then I'm saying 0.5, half of the base of the square, because I know for squares and rectangles, the centroid is exactly halfway along the base. It's like right smack bang in the middle. So I'm doing the first 4, that white gap, plus half of the base of the shaded square. That's the 4 plus 0.5 times F4. And you get 6. Okay, 6. Sorry, I just got a text message from a teacher. Great. Okay, now the circle centroid. Circle X centroid is going to be, how could I say this? I might get a little fancy here. I'm going to say 8 minus 6. Sorry. 8 minus 2. And I do that just because that's the way that it was defined in the picture. In the picture, it carefully says, it shows us that the circular cutout is positioned 2 inches horizontally in from the right. So if you like, I'm counting like 8 inches across. This is on the region number 3 diagram. I go 8 inches across, and then I come back by 2 inches, leaving me with 6 inches. That might seem a weird way to do it, but I like doing that because then if the original drawing's dimensions were to alter, then my table would still like adjust to it. Okay. If you're doing like a one-off piece of work, it's also fine to work it out and type in 6, but I recommend that you put things in terms of formulas that will update if the original information updates. Okay, so we have the 3 centroids, the x centroids for the 3 subshapes, 5 and 1/3, 6 and 6. Now, here is where we get a little schmancy. Oh, and by the way, actually, sorry, before I keep moving, those 3 numbers, those correspond to the second column in table 11.1, where he has xi measured in inches, and then he says 5.36, 6, and 6. Why does he say 5.36? I really don't like this. Instead of saying 2/3, instead of saying like I did, 2/3 of the way in from the left, he put 0.67, which is like, yeah, sure, it's roughly 2/3, but why not do 2/3? Why would you do that and then already have a slightly incorrect answer of 5.36 when we know it should be 5/1/3? I don't like that. I believe all rounding off should only be done at the end of the problem, not halfway through it. Then the error just accumulates. So, don't like that, James. Not you, James. James H. Allen III. Okay, now we're going to do a little bit of mathemagic. We are going to run this x bar down there in the green. We're going to run the x bar calculation. Hold on to your hats. Equals. Here we go. We are going to do each of the xi's times each of the ai's. Each of the individual centroids times each of the individual areas, and we're going to add them up. That's the numerator of the formula. Okay, that's what it says. See how it says sigma xi ai? That is saying multiply all the xi's by all the ai's and then add them all up. You do the multiplication first, then the sum second. So it looks like this. We do xi times ai for the first shape plus the x centroid times the area of the second shape plus, plus the centroid location times the area of the third shape. And do we keep the negative there? Yes, we do. Absolutely we do. And then I'm closing parentheses. The closing of those parentheses, that signifies the end of the numerator in the fraction. I'm not done. That's just the numerator. And I'll just keep it there for a second. Look at what's happening. We're multiplying the x centroid locations by the areas and then adding them. Under the rules of PEMDAS or PEMDAS, multiplication always happens first and then addition. That's why I didn't need to put extra parentheses in. If you wanted to, you could put it around the multiply little numbers, but you don't have to. It'll take care of it. Now we're going to divide because it's a fraction, and this is the total area. Okay? Sigma from 1 to n of the areas. We already took the sum of the area. That's what 47.2 is. So I'm actually just going to click on that cell. 47.2. That is sigma A. So I don't need to like re-add in this formula 32 plus 16 plus negative 0.785. We'll just do that. I press enter. I turn down the precision. And look at what I have. 5.55 inches, measured in inches. And here's where we decide, again, we want a common sense check. Does 5.5 inches make sense? Well, firstly, when I look at the bottom of page 140 in the textbook, it says 5.57. I got 5.55. His is wrong. His is inaccurate, maybe I should say. It's not wrong, it's just not accurate because of that silly 0.67 that he did for his triangle. Who knows where else he rounded off along the way. Bad form, James. H. Allen III. But yeah, does this make any sense? Could 5.55 be correct? So we look back at our diagram. That whole picture had a base width of 8 inches. Right? It starts at the origin, it goes across by 8. That's the extent of the drawing. So 5.55, does that feel right? I think it does. If it was more than 8 or less than 0, I'd be really, really worried. So here's my rationalization here. It's between 0 and 8, firstly. That's pretty important. Couldn't be more or less. You can't have a centroid outside the bounds of the shape itself. That wouldn't make sense. It's also approximately in the middle. Okay, centroids are generally found around the middle of things. Okay, that makes perfect sense. However, it's weighted a little bit to the, let's call it the right-hand side. Like it's a little past the middle, it's a little further than 4. 4 would be the middle. 4 would be the middle. This is a little bit past that. This is 5.55. That makes sense because, firstly, the triangle is kind of tipped that way. The triangle is heavier on the right than on the left. And also that little square block is definitely on the right-hand side, not the left. So it makes absolute sense. If I'd ended up with like, 3.0 as my x centroid, I'd be worried because that would be tipped to the left of the middle. And the triangle is not doing that. The triangle is heavier on the right hand. The block is over on the right hand. So that would not have made any sense to me. 5.55 puts us, where would that be? That's somewhere around sort of just where the white circle is beginning as you go from left to right. Okay. Actually, it's kind of in the middle of the circle, isn't it? Well, no, not quite. It's getting close to it though. No, wait. 5, no, that is, forget about it. No, it's not. It's kind of right where the circle starts. Yep. I don't think this diagram's to scale, actually. Yeah, I think that 1 inch diameter is too big. Yeah, no way is that 1 inch diameter matching to the 4 inch, so the scale is off here. I don't know why you couldn't do scale. He could have, he didn't. James, what's going on? H. Allen III. We are now going to do the same thing for the y centroid. This is the exact same calculation with a couple of exceptions. Firstly, there is no number check in the textbook. They didn't do the y. It took him a whole page to do the x, so he stopped and he said, just do the same thing all over again. For us, in our spreadsheet, it's actually quite easy. We're just going to do it right here. Well, I won't say it's easy, but it'll take care of itself. So where is the y centroid of the triangle? That's the cell I'm on right now. The y centroid of the triangle, that's where it says y1. It's like how far above the x-axis. And here's the formula that I'm going to build. Looks like we go up 4 inches of white space, and then we go up by 1/3 of the triangle's height. Now notice, okay, really important distinction. The height of the triangle, I could have said this earlier, it's not like how high it reaches up. It's how high from its own base up to its own peak, not like its total height in the air. That's important. So we are going up by 4 inches of white space, then 1/3, because that's the thick end, 1/3 in from the thick end, 1/3 of that 8-inch height. And we get a result of 6 2/3. I'm sure James would have written 6.67 and then use that. Remember that in a spreadsheet, even though it displays 6.667, it's actually using like the full perfect number in any subsequent calculations. It doesn't carry through rounding errors. That's why we love them. Okay, for the y centroid of the square, this one's pretty easy. I'm going to say it is simply half of the height of the square. I could have typed the number 2, but in case our square size would change with like a modification to the plan, I'm going to do half of the height. It is guaranteed to be half the height in the arrangement that these shapes have been set. The centroid of the circle cut out, I don't think there's any other way I can say this except just 2. I don't even need to press an equal sign. There's no calculation here. It looks like they're just defining it as being 2 inches up from the x-axis base. So that's it, just 2. Nope, not 2.000, just 2. And now again, I'm going to look down to the green. It's the exact same formula, just y values this time. Y bar equals the sum of all y centroids times areas, and then divide whatever you get by the total area. So y centroid times area plus y centroid times area plus y centroid times area. There's my numerator. Did I say denominator before? That's my numerator, and now I'm going to divide by the total area, which again I already have. Bang. Oh, I messed it up, didn't I? Anyone catch that? You probably did. I was clicking on the X centroid numbers. I don't know why. If you were wondering what I was doing, that was pure mistake. I'm just going to change the letter J to the letter I. You can always manually type references. They shouldn't have been J references. Not the J column, the I column. There we go. And I love how you can see like the colors. It highlights the ones in very attractive colors of just what you're doing, so you can keep track of it. If you ever have the same cell reference appear in the same formula, it'll use the same color. So as I glance through these colors here and I see that they're all a little different, that's what I expect. That's what I want. Okay, let's apply the same formatting. That should apply the precision as well. Yes, it does. 5.16. Now again, common sense check. I should have said maybe for X. Now I'll do a common sense check for Y. Well, firstly, I know it has to be between 0 and 12 because that's the total height of the whole shape. Okay, 0 and 12. Again, this is approximately in the middle. Halfway between 0 and 12 will be 6, and this is not far from that. It's less than 1 inch away from the 6. Okay, so that feels good. Definitely feels good. Approximately, okay. Now this one is weighted a little bit, excuse me, It's hard to talk for 45 minutes. This one's weighted a little bit down from the middle. Does that make sense? Yes, it does, because the triangle is also weighted down, not up. Like the thick end of the triangle is at the bottom, not at the top. Also, we have that chunk of square down below, so that kind of pulls it down. So yeah, I'm going to say that makes sense to me. I don't have James H. Allen III's numbers to verify, but I'm feeling pretty good about that. Now, I'll say one more comment and then we'll finish a little early. If any of you are wondering, is there an easier way for lengthy calculations? Let's say you had like 10 subshapes. Is there any better way than just typing in all these asterisks and pluses? This is advanced information right now, and yes, there is. It is called the sum product. Whoops. Sum product. And you know, I don't even need this parentheses on the front anymore because it's all going to be in here. Sum product is where you get two arrays. Okay, that's called an array when you drag select a bunch of numbers, columns, rows, blocks, doesn't matter. I'm going to sum product this array, comma, this array. That was really easy. What that does, that multiplies the matching elements in each of those two columns. It multiplies them first, and then it sums them. Okay, that's why it's called sum product. It sums the products. And it's because this thing happens so often, these sigma sums, where you have little multiplied products that you need to add up. So, way easier, and you get the same answer. If that was too complex, don't worry about it. But for those who are ready, that is a cool little trick to use. Turns out I didn't even need this one, did I? Looks like we were all good. That's the answers we want. Total area, location of the overall X centroid, location of Y centroid. You will have to imitate this, and you can copy as hard as you want. Just like, I want you to learn this. There is one right way this is going to come out, so please do it carefully on your assignment this week in your Google Sheets. Remember, that is how you submit it. I don't want screenshots, no documents. I want you to upload the Google Sheet and then click Turn In. Thanks, guys. Thanks for listening. Reach out to me if you have any questions. We'll see you later.